statistics. This is the 11.3 video. These are contingency tables, which are also, you might want to make note, basically the test we're going to use is called a test of independence. We're testing if two variables are independent of one another. Do they rely on one another or not? Dependent versus independent. So we're looking at least two rows and at least two columns of data now. So in this first problem, you can see, and this is actually the problem we're going to be using for the entire section here. We actually have 4 rows of data, and we have 2 columns of data. We have basically 2 variables that we're looking at. So the overview of this problem is that somebody had, I believe it's a stress fracture in their foot, and we're trying to figure out what is the success versus failure based off of the different options they have for their treatment. So the row variable is the treatment. Do they have surgery? Do they have a cast where they bear weight, non-weight bearing for less than 6 weeks, non-weight bearing for 6 weeks? So they've got 4 different types of treatment, and then we measure whether it was a success or failure in the other variable. So we're trying to see, is the choice of treatment independent of the outcome, or is it dependent? So that's kind of our basic idea of what we're going to be doing here is, hey, does it matter what treatment I pick? Does that influence the outcome? So we still have observed and expected frequencies. What makes this different from our goodness of fit that we did in 11.2 is that the expected is different for each cell, which is going to make things a lot more annoying to calculate. We have R, which is the number of rows, which on this first problem, like I said, it had 4 rows, not including the label row, 4 rows of data. This first problem had 2 columns of data. We need to know the rows and columns to figure out our degrees of freedom. And again, the hypothesis that we're testing, the null hypothesis, is that they are independent. So the null is basically, for this problem, it would be that the outcome does not really depend on the type of treatment that they did. So the reverse of that would be that the outcome is dependent on the type of treatment. Our test statistic is still that chi-square, and this is the exact same formula we had. That's the exact same formula that we had for the goodness of fit test. But as I said, the expected is different. The expected is where things are going to get funky. It's the row total times the column total divided by the grand total. We'll get into that in just a little bit. So again, the null in these, the null is that the variables are independent. They don't matter. One doesn't influence the other. So the alternative to that is that they are dependent on one another. P-values would have to use StatCrunch. We're going to focus again on the critical value way to do this. Notice that my degrees of freedom is rows minus 1 times columns minus 1. So for this problem, for this particular one we're doing in the notes, again, the number of rows was 4, so it'd be 4 minus 1 times the number of columns was 2, 2 minus 1. So this is really, oops, that's a 3. 3 times 1. So this problem, oops, is going to have 3 degrees of freedom when we get there. Oops, sorry about that. These are right-tailed because, again, the chi-square thing is that skewed right-looking curve. And also, all this stuff is on your green packet. Again, the formulas for the chi-square value are the same, whether it's goodness of fit or the contingency table, which is a test of independence. But the expected is a pain in the butt to do on these. So these will take longer, I assure you. We're going to do one problem and it's going to take a while. Very similar to what we looked at on the previous section. If my chi-square is in the meat of the curve, there's nothing weird. I fail to reject independence. If it's on the outside, I reject independence. So in our problem here, is the choice of treatment going to affect success of the treatment? So basically, are they dependent or are they independent? Notice we've got a significance level, 0.05. We'll get to that later. So the hypotheses, again, the null is always independent, that the variables are independent. And the alternative is that they are dependent. Before we actually start calculating all the different numbers in this problem, I want to calculate the row and column totals on this. Because those will matter. So what I'm doing, what I'm going to write here are the totals. Let's see if we can change this a little bit. Shrink this down just a hair so I've got a little room. There we go. Actually, let's make this full size for now and then we'll go back. Making all sorts of errors. There we go. Okay, so I will need these numbers, so I'm going to get them right now. The total of the first row, 54 plus 12, I'm just going to write it off to the side. That is 66. The second row's total, 41 plus 51, would be 92. Next one's going to be 73. And the last one's going to be 22. For the columns, the column of success, the first column, if I add up 54, 41, all that fun stuff, 70 and 17, I end up with 182. If I add up 12, 51, 3, and 5, that adds up to 71. Again, I will need these numbers. I also need the grand total, which would be adding up all 8 numbers. If you add up all 8 numbers, I believe you get 253. 5 in the middle there. Oops. Come on. There we go. There we go. So I will need all these numbers when I start calculating stuff. So now I've got those. Oops. So I've got to start calculating basically for each row and each column the numbers that are going to add up to be the chi-square. So remember that the formula for the chi-square is the sum of each observed minus expected squared over the expected. Okay, we'll do the sum part at the end. So right now we need to focus on this. And I need to do this for each individual cell. So what am I actually saying here? For my first cell, row 1, column 1, 54 is the observed value. So it's 54 minus, here's where it gets funky. The expected, I have to calculate off to the side. The expected is the row total, so the row that 54 is in, 66. The column the 54 is in is 182. I have to divide that by the grand total, 253. And again, just a reminder, what I'm using is this: row total times column total divided by grand total. That's to get the expected for just this cell. If I run those numbers, that gives me an expected of about 47.478. Squared on top. There we go. So again, the highlighted stuff over here, I'm doing that with just this first cell. If you run those numbers, if you run this calculation, that will give you about, and we're going to keep rounding to 3 decimals on all this stuff. That's going to give you about 0.896. So I like to do this for each row and column. So this was row 1, column 1. That's what I calculated out. Okay, I'm going to go row 2, column 1. So now I'm going to look at row 2, column 1. So 41 is the number. So I reset all of this mess. Oops. And I do it all again. You can see this is going to take a while. So the observed value for row 2, column 1 is 41. The expected is what I have to calculate out. So the row total that 41 is in is 92. The column that it's in is the first column, which is 182. The grand total again was 253. That calculates to an expected of about 66.182. That goes in for E, which notice that in the formula, E is in 2 spots. I run all this in my calculator, and this gives me the value that I'm going to use in row 2, column 1, which is about 9.582. All right, we're getting there. Now we got to go to row 3, column 1. So row 3, column 1. The observed is 70. I've got to calculate the expected. The row that number 70 is in has a total of 73. The column has a total of 182. The grand total is 253. This will give you an expected here of 52.514. I run all these numbers. Oops. I run all those numbers, and that gives me the value that I'm going to use for row 3, column 1, which is 5.822. Let's actually jump to a different one just so you can see how I do it depending on where I'm at. Let's say I was doing row 4, column 2. I obviously would keep going in order, but I'm not going to do all these individually. So let's say I jump to row 4, column 2. So row 4, column 2 is the number 5. So if I was running the calculations for that, the observed is the 5. The expected is the row that it's in, which has a total of 22. the column that it's in, which has a total of 71, the grand total, which is 253. So the expected here was, if I run those numbers, 6.174. If I calculate this out for row 4, column 2, that gives me a value of 223. I'm just going to give you the other 4, but you would follow the same process. So for the other 4, row 4, column 1, if you calculate it out, it's 0.087. I'll just write down the rest of these, 2.297, 24.562, 14.925. Okay, so those are the individual values. I'm going to now sum those up to get my actual chi-square value, which if I add those up, so I'd be adding all these up, you should get a chi-square value of about 58.394. That's my chi-square. Now realize on this problem, this was a huge problem. 4 rows, 2 columns, that's massive. On your exam, it will not be as big of a table. But if we can do this, the exam should be easy. Okay, so my chi-square is 58.394. Now, I get the critical value as well. So as I talked about, the degrees of freedom were rows -1, columns -1, which was 3. My alpha was 0.05. So 3 degrees of freedom, 0.05. Going to the very back of our packet. 3 degrees of freedom, 0.05 was the area to the right. So this goes with 7.815, which is my critical value here. So if I think of this graphically, my critical value, the number that separates normal from weird, was 7.815. Anything beyond that is weird. Remember that I got a chi-square that is massive. So my test statistic is way the heck over here in the critical region, for sure. Super, super far over. So that is very weird. Weird means reject. So we reject the null. Had we used technology, which don't worry about it, because we won't be doing that on the test, your p-value is super duper small. Remember, if the p is low, the null must go. So either way we slice it, oops, that is way too small. That's way too big. Let's try this again. Learn technology. There we go. Either way, we reject the null. Now, what's important to remember is what the actual null is. The null was that these two things are independent. So we are rejecting independence, which sounds weird, but rejecting independence means basically we are saying that they are dependent. So going all the way back to what actually is happening in this problem, what were we testing? We were testing, does the choice of procedure or treatment, does it affect the outcome? They are dependent on one another, so yes, they do affect it. And we can see this. Surgery, pretty good, success to failure. Wearing a cast, really bad. Basically, I'm sorry, wearing a weight-bearing cast seems to be really bad. More failures than successes. Wearing a non-weight-bearing cast, so not putting weight on the foot for 6 weeks, almost everybody, almost 100%, almost everybody succeeded doing that. Wearing it for less than 6 weeks, not a whole lot of data on that. But yeah, there definitely is some sort of relationship here where your outcome does seem to depend on what you picked. And again, back to the last slide, it doesn't tell us what treatment is best. We can see that the choice of a non-weight bearing cast for 6 weeks had a almost 96% success rate. So seems like that's probably our best option. Again, the null is kind of bizarre in these problems. So you've got to really think your way through it. If I'm rejecting independence, I'm saying that the two things are dependent. One is influencing the other. Okay, that does it for 11.3 notes.